Hello everyone, this video is about the conjugate gradient method, which is an efficient method for solving large sparse systems. Here we will see that solving a system of linear equations is equivalent to minimizing this scalar function, where the matrix A is symmetric and positive definite. The scalar function is minimized when its gradient, which is equal to ax minus b, is 0, which is the same as the matrix vector representation ax equals b. We start with the initial guess of the solution vector, then we compute the initial residual. We can then set the initial search direction to be the same as the residual, which we can see is in the direction of steepest descent. We then compute the step size that we want to take in the search direction. Now we have the solution vector at iteration k, the step size and the search direction, so we can update the solution vector by moving along the search direction by a distance equal to the step size. The next step is to compute the residual and check if the residual is smaller than a user-specified threshold. If yes, we stop the iterations and output the solution vector. Otherwise, we continue and find a new direction that is conjugate to the previous direction. Then, we repeat these steps from computing the step size until a stopping criterion is met. In theory, for a system with n by n matrix, the conjugate gradient method should converge in at most n iterations. To implement this method, we write a conjugate gradient function which, like Gauss-Seidel function, takes the coefficient matrix A, output vector B, and the initial guess of the solution vector as key inputs. On line 313, we compute the initial residual, and then in the following line, we set the initial search direction. On line 317, we start the loop, which will run until the maximum iterations or the threshold criterion is met. On line 320, we compute the step size, and on line 322, we update the solution vector. Then on line 325, we calculate the new residual and then check the stopping criterion on line 328. If this criterion is met, we return the solution. Otherwise, we calculate the new direction, which is conjugate to the previous search direction on line 333, and continue the iterative process until a stopping criterion is met. Let's now use this code to solve an example where the 3x3 coefficient matrix is symmetric, positive, definite. In this case, we get the correct solution in 3 iterations. Thanks for watching. I hope you liked this video. Please subscribe and see you in the next video.